My name is Adrian Hetman, and in today's presentation I will talk about the most popular smart contract vulnerabilities, and we'll try to answer the questions: are smart contracts haunted? So let's start. Agenda for today: I will give you an introduction about myself, what I've been doing and what I'm currently doing. Next we'll dive straight into the topic itself, the most common vulnerabilities in smart contracts. I will give you also some examples of those vulnerabilities, and I'll do an outro, basically sharing some cool links that you can use for your own learning purposes. And one thing that I want to mention: this presentation will also serve an additional purpose. I want to teach you something more about the smart contracts itself. So when you use those links that I will show in the outro, you can better understand the most common vulnerabilities presented here. Okay, let's start. So, my name is Adrian Hetman. As I said, I'm a security researcher at Immunefi. I've been also a content creator at Immunefi, meaning that I've written in the recent 7 or 8 months multiple postmortems that can be found at our Medium, and I've been very active on Twitter. Previously, I worked as an auditor of smart contracts for over a year, and previously also I worked as a smart contract developer since 2017. So, the common smart contract vulnerabilities. We have 3 major types that we'll go over. First, we have unsafe external calls, we have usage of spot price, and we have authentication issues. So let's start with the unsafe external calls. Before we dive into that, we first need to understand what an external call in a smart contract really is. Well, it's a call to a third-party address that we do not control, meaning that if the recipient is controlled by an attacker, every external call is potentially dangerous, because the attacker may be able to force your contract to transition into undefined state. So what does it mean really? Well, if we have a function that allows you to withdraw or to deposit, or basically takes any argument, and one of those arguments is an address provided by the user, and later on we do something with that address, meaning either we send funds to that address or we perform some function calls on that address because we believe it may be a smart contract, another smart contract that we may expect. In those cases, it is a third-party address and it is really an external call, and we may expect that after such a call, our system may be forced to transition into undefined state. And one of such examples is a re-entrancy attack. It's really simple, and I believe one of the oldest types of attacks in smart contracts is an attack where malicious user can recursively call a vulnerable function to steal funds. And that type of attack was really the attack vector behind the DAO hack in 2016 that has led Ethereum to do a hard fork. And because of that hack, we now have Ethereum as we know it, and we have an Ethereum Classic that still believes that everything that happened in the DAO hack should really happen. And on the Ethereum Classic, the DAO hacker is really a wealthy guy over that chain. Okay, so how an re-entrancy attack may look like. So we have such a basic function like withdraw balance. It's a public function, meaning that anybody can call that. That withdraw balance is, let's say, in a escrow contract, meaning that many people can deposit their Ether to that function, to that smart contract, and later on, if they want, they can withdraw everything that they just deposited. So to be able to know how much that function needs to send to the caller is message sender. That's the address of the caller. we check the mapping of the user balances to the address. We get that value, then we send to that address the amount to withdraw. We check if it is successful, and at the end, after the call has happened, then we zero out the balances. Seems simple, right? But the trick here is that in Ethereum, in smart contracts can act upon receiving an Ether. Meaning, whenever I send an Ether to a smart contract, that smart contract will run their fallback function and will do some and will execute some logic. And in that case, if the message sender is actually a malicious contract, and from that malicious contract we deposit it to an escrow contract, then we withdraw balance, then on that second line, meaning when we send the actual funds to the message sender, we will execute the fallback function, and inside that fallback function, we will call withdraw balance again. And we will check the user balances again. And they are still unchanged because the line that changes is after the call has happened. And we are re-entering the function before the function logic can ever go to the user balances. And thus, we can re-enter as many times as we want, basically draining the contract. And that's a very simple example of re-entrancy attack. And now we can look at the real-life example in an AMM project. In various AMM projects, we have a harvest function, which basically allows us to gather all the accrued rewards tokens that we have for all the LP owners, but we don't want to dive into that. But what's really happening here is updating the state of the pool. That's fine. We're reading all the user info of the caller. We're calculating the pending rewards, and we're doing a safe token transfer, and then we're updating some state variables. And as you can see, we basically have the same type of issue, but more complicated. The example is a little bit more complicated, but the issue itself is really the same. First, we're executing the token transfer to the message sender, and then we are updating the states. And if that would be an ERC20 token, that wouldn't be an issue, because whenever a contract receives an ERC20 token, it cannot act upon receiving that, unless it's a special type of token standard, but we won't dive into that here. But what's really happening in that concrete example is that underneath, we are sending the wrap ether, meaning the ether in a representation of ERC20. We unwrapping that, meaning that at the end, we're sending ether itself to the message sender. And by this, smart contract can act upon receiving the ether, re-enter harvest function, and drain the contract from all the rewards. Basically drain the contract, not from the rewards, but in general, drain the contract. Why? Because in the pending calculations, we are subtracting from the user share the user reward debt, and that is updated after the safe token transfer, which, as we just learned, isn't really safe. So if something is called safe in smart contracts, don't believe it is really safe. And one of the things, here's basically the explanation and summary of what I just have said. How to overcome that issue? Well, we follow checks effects interaction pattern, meaning that first we do all the checks that we need. For example, if the user really have funds that he wants to withdraw, then we update all the states, meaning all the effects that would happen after the interaction. In that case, we're updating the user balances. in the first example, let's say we update them to 0, and then at the end we're performing an actual transfer of funds, meaning the interaction. Another example how you could avoid that issue is by using re-entrancy guard. That is a smart contract modifier in Solidity, written by OpenZeppelin, or basically you can write that yourself, where a function can be called only once in a transaction. You cannot re-enter that. Okay, but I'm slightly going off track. Let's continue. Next type of bug, which is my favorite type of bug, is an initialized proxy bug. Before we dive into the bug itself, we need to understand what a proxy contract really is in a smart contract. Proxy smart contract came to existence because of the inherited some call issue, but really it's a feature of the blockchain that everything that we put on the blockchain is immutable. And that also includes all the smart contract code that we deploy to the blockchain. And as we know, through software development, you cannot check and anticipate to remove all the bugs before actual deployment and release of your project. There will always be some bugs left that can be exploited by hackers like you. So to overcome this, there is a proxy contract, which, yes, everything still is immutable at the blockchain, meaning that whatever we deploy to it cannot be changed, only deleted. Meaning there's a special opcode and function in Solidity called selfdestruct that can zero out all the bytes of the contracts in the blockchain, which is really also important in that bug. But I will come back to that in a second. So a proxy contract works like this. We deploy our proxy contract, which will redirect all the calls to that proxy contract to the implementation contract. And that implementation contract what really does is serve all the code, all the logic that we need, and that logic will be executed in the context of the proxy contract. And how does that help us? Well, if we find a bug in our implementation contract, meaning that withdraw function, for example, has a re-entrancy vulnerability, we want to fix that. And how do we fix that? By redeploying the implementation contract, and in the proxy, we're just the admin of the proxy can state that, okay, please, from now on, that proxy contract will point to the new implementation. And it's really simple as that. There are two approaches to the proxy upgradability pattern. First is a transparent proxy pattern, meaning that all the logic for upgrading the proxy is within the contract itself. Meaning that, yes, we have a proxy contract and an admin can call special functions on that proxy contract, mostly called upgrade to, and call, etc., etc., or authorize upgrade on the proxy contract, and the implementation contract would be changed. But also we have something like UUPS, proxy upgradable method, meaning that all the proxy, all the upgrade logic lies in the implementation contract itself. Why? Because it's cheaper based on the executed gas costs. Because when we're forwarding all the calls from the proxy to the implementation, we need to check who the caller is. If the caller of that proxy is really an admin or a normal user. And that adds to the execution cost. But I'm slightly going ahead of myself because I will talk about that in the next slide. But knowing all of that, let's read what we have on the slide. So initialized proxy bug only applies to the UUPS style proxy bug, and this bug can lead to the self-destruction of the implementation contract, which could render the proxy contract useless. And this is because of the aggregatable proxy pattern used, one with the aggregate logic residing within the implementation contract rather than the proxy. Meaning that if we basically we can destroy the implementation contract, render it useless, because as we know, there is a special function in Solidity and Ethereum called self-destruct that zero outs all the bytes of the smart contract, and then the proxy would just point to nothing, and we couldn't upgrade the implementation to another address because all the upgrade logic lies within the implementation contract itself. But how can one really destroy such a proxy? Well, first we need to understand what a call to a contract really is, because we will need to discuss the delegate call. So EOA is basically a user controllable address, like a wallet, and the user calls a contract. And in the context of the contract A, the message sender, the caller, is an user address. The message value, meaning how much we send Ether alongside it, because maybe some function requires some payment. It's the value that we send alongside the EOA call. And the storage, meaning that every, for example, balance updates will be reflected in the contract A. That's cool. And if the contract A would, for example, call a contract B, then, EOA calls a contract A, which later on calls a contract B. The contract B message sender would be the contract A address, not the EOA, because the contract A calls contract B. Message value would be the message value sent from the contract A. And the storage, meaning if something changes here, for example, we add two numbers together and the sum of that would be stored in the contract B. Pretty simple, pretty straightforward. But now we have also a delegate call. Delegate call works almost like a call, meaning that let's say we have a proxy contract which uses a delegate call to implement the implementation contract. If a caller would call a proxy contract, then through the delegate call in the implementation contract, in logic contract B here, the message sender would be the caller itself, not the contract A, because we're just forwarding all the calls to that. Message value would also be the same, and storage would be the storage of the proxy contract, not implementation contract, meaning that the implementation contract really what it does is serves as all the logic that we're using executing in the context of the proxy contract, and all the state changes, meaning all the balances, all the sums, all whatever we are doing with a contract is reflected not in the implementation contract but in a proxy contract. So, as we have in the second point, the proxy contract runs contracts B's code as its own, modifying the storage and balance of contract A. So, how we can use that? Well, if the proxy contract... Okay, all right, we have an example coming right up, so I will show you how you can destroy the implementation contract yourself. So, one additional thing that we need to understand before we go into a real life example is a constructor and initialize. Constructor is a default function, a function that is run during contract creation. When we deploy a contract and we want to set some initial state to some variables like a token name, total supply, etc., we can do that in the constructor itself. And constructor is only run once during contract creation. But constructor doesn't really work in an proxy situation, because we want to reflect all the state changes in the proxy, not in the implementation contract. So to overcome this, so when we deploy a new implementation after an upgrade, we want to initialize that implementation with some basic changes that contract needs to have. And just to overcome that, we have an initialize function, which proxy can call. I mean, the admin of the proxy can call on the implementation contract, and all the state changes would be reflected on the proxy contract. And initialize function is also written in such a way that it can only be called once. And here we're coming to our to our first example. I know I talked a lot during the proxy example, but it was really, I believe it's really worth it, and without it you wouldn't be able to really understand what was happening here. So we have a contract, my token, that inherits from the OpenZeppelin's framework, all the ERC20 upgradable stuff, etc. We have the initialize function that I talk about. We have the modifier initializer, which checks that the initialize was only called once. We have authorize upgrade, etc. Everything in its place. But the issue is that yes, initialize was called from the proxy, but what if it wasn't called on the implementation contract itself? Because please remember, yes, we are calling the implementation contract from the proxy contract, but still everything on the blockchain is publicly available, meaning that we can still access the implementation contract by themselves. And we can call functions on the implementation contract. We wouldn't really achieve much because everything is reflected in the proxy contract, not in the implementation contract. But if the implementation contract has an initialize function and that function hasn't been called on the implementation contract, we can call it ourselves, meaning that we can become an owner of that contract. And by being an owner of the contract, of the UPS style proxy, we can authorize an upgrade. And we can upgrade to a malicious implementation. And that upgrade is done via delegatecall. And on that upgrade, we are calling initialize function. And that initialize malicious function will call a selfdestruct, meaning that by upgrading to a malicious contract, we would self-destruct my token and the proxy would just point to nothing. So here's a step-by-step exploit situation. Implementation contract isn't initialized. An attacker becomes an owner by calling an initialize function. As an owner, the hacker can call upgrade and call directly on the implementation. Upgrade and calls an immigration initialize function on a new implementation using delegatecall. And in a result, the implementation contract executes a malicious function that calls self-destruct and renders the implementation contract useless. And what's really also interesting about this example is that OpenZeppelin is really well-known and in general secure framework that many projects are relying on and many developers are relying on because they have really thorough security reviews. But still, if you as a developer are relying on any code that you haven't written, and I'm not saying that the code that you are writing is 100% secure, but you still can potentially anticipate an issue in the framework that you are using that will affect you. Luckily, in this example, the fix was simple because we simply the owners of the contract would need to call initialize on the implementation, and that was it. But through that bug, nearly 200 projects were affected. And also, luckily, none of those projects were harmed by this. Because what would happen if we destroyed the implementation? Well, all the funds that, for example, were stored in the proxy contract are stored there forever. We have no way of extracting them. Basically, the project at that moment is dead, is bricked, basically. And we cannot do anything with that. Another cool example of the uninitialized proxy is a HarvestFinance. I won't talk about that because it works very similarly to the OpenZeppelin one, but the team, DDoP team that has found this bug did it in a really cool way. Meaning the HarvestFinance didn't have their contracts verified on the Ether scan, meaning that no, sorry, I take that back. They had, but DDoP team managed to find this issue by analyzing the blockchain data, meaning analyzing the bytecode. And in the bytecode, I mean the bytecode of the contract, which yes, wasn't actually verified on the Etherscan, they managed to find an initialized proxy bug. And here's really a good explanation of how they did it. You can simply find that article by typing HarvestFinance initialized proxies bug fix review. Okay, moving on. Spot price usage. Sorry, I was taking a sip of a coffee. Yes. So, before we understand this bug, as usual, we need to understand some basic terms. So what are the price oracles and why we even need them in a blockchain system? In a blockchain, all the smart contracts, they really can only talk to each other. They cannot call any external APIs, meaning they cannot check on the Google the price of the Ethereum if a project needs to. They need to rely on on-chain oracles to do that, or off-chain oracles. And basically a price oracle, and oracles in general, are such a tools that inject data into the blockchain of some real life information that a project may need. And a price oracle is a tool used to view the price information of a given asset, meaning if we want to view the price of Ether, it will be $2,800. So, and there are many projects in DeFi ecosystem that are relying on the price oracles. And there are two approaches to that, as I said. There are on-chain oracles, which rely on the constant products AMM, like Uniswap v2 or Balancer or SushiSwap, etc., etc. And they can check the price by checking the ratio of the pool. Meaning, if we have ETH and DAI pool, and DAI, for those who don't know, is a stable coin pegged to $1, and that ratio gives us the current price of Ether. Pretty cool, right? And how can we be certain that the price in a pool is reflecting the on-chain, is reflecting the real life information? Well, the arbitrageurs will really fight for that because every such price movement, it is a possible spot for them to earn some additional money. Okay, but we also, as I said, have an off-chain oracles like Chainlink, which has their own decentralized network of trusted verifiers and nodes that are feeding the Chainlink network, which we can actually query from the smart contract, meaning because they are really another smart contracts on the blockchain, on the Ethereum, and that would also provide us with the correct information. But going back to the on-chain oracles and that ratio of the two tokens, it looks really simple. It is in general, constant products AMMs on blockchain are awesome invention, but the issue is that the price that we are checking is the spot price, meaning the price at the very moment of a transaction, and it only consists of a ratio of 2 tokens. But what happens if we would unbalance that ratio? Then the price wouldn't be right. And if the price isn't right, then we can use that as a potential entry point to a product, to a DeFi project, and exploit that, usually stealing a lot of millions of dollars. Okay, but how can you change the ratio of, for example, the ETH and DAI? Because currently it holds a lot of ETH and a lot of DAI, so it would take really some whale users, meaning the user that holds a lot of cryptocurrencies, they're basically crypto millionaires or billionaires even, to move that price. Luckily, DeFi came with a solution. We have flash loans. So flash loans are a way to borrow a large amount of money from lending protocols like Aave without collateralization, meaning we don't need to pay for that. And the borrower pays just a certain fee at the end of the transaction. But the caveat is, with the flash loan, is that it needs to be returned within one transaction. If not, the transaction will be reversed. So why have something like that? Because if there are some strategies, yield strategies or strategies for arbitration, and you need really large sums of money, you can use that. But you can also use a flash loan to change the ratio of the pool, and by that changing the spot price of the token, one of the tokens. And now we come to the first example, Yearn.Finance. So at this time, I mean, maybe not at this time, but because this is still one of the most common vulnerabilities stock, but still many projects switch to different type of checking the on-chain price. They're relying on a TWAP, time weighted average price. But I won't dive into that. I just wanted to say that there is a solution to that. So, Yearn.Finance. Yearn has vaults that let user hold an asset they like while also earning yield denominated in that asset. So they can grow their stack and earn more money, basically. So this bug was in regards to vault for USDT. USDT is a stablecoin. And how the vaults also work is that they have multiple strategies. And a strategy is, well, a trading strategy, a smart contract that basically has all the logic on how to make the best trades to earn more money. It's a really cool project, but what also is really interesting about their finance is that they are really one of the older projects in the DeFi ecosystem. They're well respected, their development team is really excellent, but still sometimes issues can slip through. Even something like spot price usage, which is quite common and quite easy to catch. So we have a withdraw function. We call that function is on a vault. We can withdraw that. We liquidate our position, take all our profits. In the liquidate position function, there's another functions calls, but in the end we also call the sell BPT for exact token. And in here, in the exit pull request, we basically burning our position in a pool to get the USDT tokens, but we do not check the price of that USDT, meaning that we can manipulate this pool where USDT is residing, where we have our share that we are burning to get that USDT back. And by manipulating the pool, we are able to trick the system into burning more tokens than it should, into basically returning the amount that they usually would need to burn a much less tokens. So let's see how that would go. So first, we flash borrow YVUSDT and DAI from Bento Box. Bento Box is from SushiSwap. And one additional comment, this bug was only possible due to the fact that there was almost 41 million YVUSDT to be able to be flash borrowed. So, and the vulnerable strategy would be only called if we withdraw a lot of money, which was only possible in that one scenario. And of course, the bug is fixed right now. So we flash borrow YVUSDT. We buy USDT with DAI at the balancer to imbalance the pool. We withdraw from YVUSDT. Withdrawal will sell more balancer LP tokens due to the imbalance pool because of the second step. Then we buy DAI back with USDT to get a profit, meaning that pool is slightly more balanced because of the previous step, and our DAI is worth a bit more. I mean that it's not 1-to-1. One DAI equals to 1 USDT. It was 1 DAI equals 0.9 something USDT. But by borrowing many millions of DAI and of YVUSDT, we were able to get in that hack around 6 or 7 millions of dollars of profit. We deposit back to the YVUSDT and we repaid the flash loan. And all of that has happened in one very complicated transaction. Okay, moving on. You have lack of authentication. So we have these two functions. The first one is for unpausing, and here is the just this one function in general. And pausing is used in situation where, for example, we found a bug or something is exploiting our protocol and we want to be able to block the hacker to further exploiting our protocol. So we are pausing the protocol. But the function unpause can be called by anyone. Simply they forgot to add only owner modifier, which allows only the owner to call the unpause function. So even if the project would pause the protocol, we would be able to, the hacker would be able to call unpause right after that and continue with their hack. Simple as that. This example is a bit more complicated in a sense that there is a lot of code, but the issue is similar. So we have the match order. This function was from some NFT project, NFT marketplace, where you can sell your NFT, and at the end you could, for example, match the order that was based on your NFT. All the checks are done. We're sending all the information in the functional arguments. All is fine, and at the end we check if the order was cancelled. I mean, cancelled or finished. If it basically this needs to return false. All is good. But in Ethereum and many other EVM-based chains and other chains as well, we have something like a mempool, meaning when we submit a transaction, that transaction isn't executed right away. It needs to be included by the miners to the blockchain, but before the miners pick which transaction they want to include, all the transactions from all the network is residing in a mempool, and that mempool can be investigated by anyone. So a hacker seeing the match order function could, for example, front run the match order function and call the cancel order before the match order has really happened, and would cancel that transaction. How? Because those two arguments are exactly the same as the one that the owner of the NFT provided in the match order function. And there, as we are dealing with the front running and accessing the mempool, we also can get all the arguments used for the match order, use them in the cancel order, set a really high gas price for the cancel order, so the miners would be incentivized to include this transaction first. It doesn't really matter what is happening here. Really, what is important is that we have the order hashes set to true, and by that set to true, this required statement would fall, meaning reverting the transaction, meaning that the owner of the NFT won't be able to sell it in that match order. They could, of course, set it again for sale, but the issue would still be there. So how they could prevent such an issue? Well, all the checks that are happening here, all the ECDSA signatures, elliptic curve cryptography checks done here on the sender, I mean, are not performed here. If they would also, the cancel order would be also be possible to be only called from the owner of the NFT, then it wouldn't be an issue. And really, that's it. So those three categories and some small subcategories were are really the most common smart contract vulnerabilities that I've seen in a Web3 security space in the past 2 years. Really, they are still pretty common because there are many new developers coming into the Web3 space, and sadly they're copy pasting the code from other projects without realizing what they're really copy pasting, without understanding what they're copy pasting, how the code is working, and even if they're not doing that, they don't have the best knowledge of the security incidents that has happened in the past few years. And because of that, there's an, let's say, opening for becoming a Web3, of course, white hat hacker. And here are the useful links that can get you started. The first one is Solidity by example. If you want to learn Solidity really fast, learn on some really useful examples and go from beginner to intermediate really fast. That's your resource. Plus, the creator of the Solidity by example also has a YouTube channel, which I forgot to list here, but All the links to that are also on this website, and on his YouTube he goes even deeper in explanation of certain things, and also present some DeFi related logic explanations. Next one, we have an awesome DeFi developer roadmap created by Officer CIA. If you are more like a CTF styled person, there is a damn vulnerable DeFi XYZ. This is what is awesome about the CTF is that it deals with real life examples of, I mean, as closest to real life as it can get in a form of a CTF. So I highly recommend that one. And there's also an amazing article written by C. Michael on how to become a smart contract auditor. I highly recommend that one. And on the notonlyowner.com, there is a gathering of all the other resources that I haven't mentioned here in regards to hacking smart contracts on Ethereum. And really, that's it. So thank you for listening. I hope that you enjoyed that, and I really hope that you learned something. If you have any questions, you can just find me on Twitter and send me a DM. Thank you very much.